I do want to do a question from your previous exercise because I had a few students ask me about it, just in case you didn't do it. The question is, find all the stationary points from here and then find the nature of it. So in order to do that, as we know, to find the stationary point, what do we got to do? We have to differentiate it. And then from here, if I want to obviously solve for 0, solve for x, that's this equals to 0. So from here, x is equal to 0. From here, what do we have? Plus or minus 1. Yep. Now, as I told you, to find the nature, you use table of values with the stationary point in the middle. But this is what I wanted to point out. Because you know how I said last lesson, the value after the middle point, you want to pick a value just after that point. In this case, that would be 1. But in this case, you don't want to do that because 1 is a stationary point. So you can't use that value. So I would prefer to use 0.5. You're allowed to use decimal. Okay, that's the point I wanted to make. So similarly on this side. Okay, so if you obviously substitute 0 in here, you want to get 0. If you substitute 0.5, you want to get, I'm just going to write out the values, okay? This is increasing. That's going to be 0. So give me a number here after 1 that would be appropriate to use. Yeah, it doesn't matter. You could do 1.1, 1.2. I use 1.5. This one, as you can see, I can't use 0 because that's already a stationary point. So what I used was 0.5. Okay?
Yeah, but if you go from 1 to 2, it's not 1.
I can use 2. That's fine. I can.
0, 1, 2.
Because 2 is not a stationary point. I just wanted to pick a value close to 1, which is like equally close to the number before. It's up to you. Minus 1, as you can see, the number below minus 1, above minus 1 is 0. I can't use 0 because I have a stationary point there. So minus 0.5 is fine. So my point is, in this one I can use minus 2. Yeah, because there's, yeah, that's my point. So based on this, I have this, this, and this, okay? Now, today's lesson, we can find the nature of the concavity of each stationary point without using table of value like this. And the quick way is to actually just substitute it into double differentiation, all right? So if I differentiate this again, I get this. And from here, if I substitute these stationary points into double differentiation form, so if I substitute 0, that's obviously minus 4, yeah? If you get a number less than 0, it's concave down. And as you can see, that's the case when I put it into table of values here. Same thing, if I substitute 1 in here, that's 12 minus 4, which is equal to 8. That's a number bigger than 0, so that's concave up. And as you can see, at 1, I have concave up. Same thing for minus 1. If I sub it in, I'm just going to give you the answer. You're going to get 8. That's also bigger than 0, which is concave up. So that's the quick way of finding the concavity. Just substitute it into double differentiation form, and that's the note that I write here. Now, point of inflection can also be found by solving for f double dash x. I've briefly explained what point of inflection is last time, but I'll explain it again. But let me just solve it first. So if I make 12x squared minus 4, because that's the double differentiation form, equal to 0, if you solve for this, you're going to get 1 over root 3. As a decimal, this is plus or minus 0.6. So girls, if I want the point of inflection, POI I like to call it, what I have is basically this, and if I substitute plus root 1 over 3 back into the original, because I need the y coordinate, you're going to get a number roughly like this and this. So let's actually put it all together and actually sketch this out. What does all of this mean? Let's start by plotting the stationary point. The stationary points are sorry, I forgot to write the actual coordinate. At -1, I think it's, sorry girls, I didn't write this down. At -1, what's the point? How do I get the point again?
0.
If I put it in here, is it 0? No, it can't be. 1, sorry, -2, -3, or -4. Let me just get the full point because I forgot to do that. And here, okay, so at -1 and -4, let's say -4 is here. At that point, what's the nature? Concave up. I'm going to do 1 and -4, so 1 and -4 at that point. It's concave up again. And at 0 and -3, so at 0, let's say -3 is here. It's concave up. So the graph is going to look something like this. Something like that. Okay? And this point of inflection here, what that is 0.6. Let's say -0.6 is here and -3.6 is here. That's the point of inflection that I've just found. Okay? And likewise here. That's positive. Okay? Did you see the picture? Remember, point of inflection is the midpoint between where the concavity changes from, in this case, minimum to maximum. Okay? So as you can see here, it changes from maximum to minimum. So that's what point of inflection is. Okay. Now, an extra key note. Sometimes, not all point of inflections exist. You actually need to check if it is a point of inflection, and that's best demonstrated with this example from your textbook. So this is another question now. It says to check if this has a point of inflection. So let's differentiate it twice, because point of inflection, you differentiate it twice. And then you make it equal to 0 to find the point of inflection, remember? So from here, x is equal to 0, and if you substitute that back into the original, you get y equals to 0. So this is your possible point of inflection. Now to check if it is actually a point of inflection or not, I wrote a note here. You got to use table of values. So, but with this table of values, to check for point of inflection, you actually substitute it into double differentiation form, which makes sense, right? Because you're finding the point of inflection from double differentiation. So once again, get the point of inflection in the middle, get a value after that, and get a value before that. Obviously, if you substitute 0 back into double differentiation form, you're going to get 0 because that's where you got the point from. But if you substitute 1 in the double differentiation form, what do you get? 12 here. And if you substitute -1 in here, you also get 12. And here's the problem. Yes, that's 0, but see how they're both positive? You got to have two different signs for it to be a point of inflection. So that's how you know it's not a point of inflection. There's got to be change in sign if it's a point of inflection. Okay? And girls, this can be actually seen by graphically. Do you girls remember what that looks like? If you have an even power, it's always going to be parabola. And can you see from here, this possibly cannot have a point of inflection. Because for you to have a point of inflection, you need to have like another curve where it changes from minimum to maximum. This just has minimum. That's where it ends. That's all it is. So it cannot possibly have a point of inflection. Does that make sense? Okay. Example 6, if you are looking at it, it says find the stationary point and its nature. All right? So to find the stationary point, once again, what do I need to do? Differentiate it. I can then make it equal to 0. So obviously x is equal to 0. And then y is equal to -3. All right. So like I said, if you want to determine the nature of a stationary point, instead of using table of values, what did I teach you to do? Differentiate it again. Now, here's the problem. So to find the nature of a stationary point, what do I need to do with a stationary point? Sub it into the double differentiation form, right? But here's the problem with this one. You get 0. Then what the hell does that mean? Okay? So what that means, if you substitute and you get 0, it's a possible horizontal point of inflection. Alright, do you guys remember from last time what a horizontal point of inflection is? It's when you have something like this. Okay? Let's see so how do I test if it's a point of inflection? What did I tell you here? What am I putting in the middle? What am I testing right now? 0. So if I sub 0 in here, obviously that's 0. If I sub 1 in here, 40. But if I sub minus 40, minus 40. So as you can see, there is actually a change in sign. It's negative, 0, and positive. What this actually means when you get a change in sign like that is when you have negative double differentiates concave up, because I think I've shown you that in the beginning of the board. Because when I said, because remember, yeah, so this is what it means. So it is a point of inflection, but it's a horizontal point of inflection, which more specifically looks like that, but actually 3 units down. So it's actually this. This is what the graph actually looks like. So, girls, this is what I mean. Horizontal point of inflection, okay? With horizontal point of inflection, that's a property that you need to know. So with horizontal point of inflection, you need to test it out. Because when you sub it into the double differentiation form, it won't give you a number that's bigger or less than 0. So use it using table of values. All right, so can you see here on this side, that's the maximum side, and this is the minimum side. Do I need to show example 3? I think that's enough. All right. Yeah, it is. Yeah. All right, I'll stop now. Thanks, girls.